Okay, so Lenz's law states that the current through the loop will set up in a direction such that the magnetic field of the loop opposes the change in magnetic flux. What in the world does that mean? Okay, so I'm just going to draw it out for you. Alright, so let's take the case where we have our hula hoop and it's flat in the room, so I'm trying to draw that so you can see it kind of horizontally. And we have a magnetic field that is directed from the ceiling to the floor. So there's our magnetic field. As I rotate it, so I'm going to show you the next picture. It's like a cartoon, like a series of pictures. We're going to rotate it. We have decreased the flux. We had a maximum flux. Now we have somewhere between the maximum and the minimum. So the magnetic field of the wire is going to oppose that change. So there's a decrease in magnetic flux down through the loop. So the wire is going to make up for that loss, and I'm going to use a blue color here. So the wire will create on the inside of it a magnetic field, I drew that the wrong way, to make up for the loss. So it will create a magnetic field in the same direction. So you take your magnetic field fingers that curl around a wire, and you stick your magnetic field fingers down into that loop, and you grab that wire. So your fingers are the magnetic field created by the current carrying wire, and because of the rotation, we're losing magnetic field, so the flux is decreasing. So to make up for that decrease, we're going to add some magnetic field. We're going to add some B to counteract the change due to the change of theta. So when you put your hand down into the loop and then grab the wire, your thumb should be pointing in the direction of the current. So it would run to the, like this way around the front, and then that way around the back. That would be the direction of the current. Okay, so now let's take the case where we start and there's no magnetic flux. So we're going to look at the magnetic field is straight down again. And we'll practice these in some other orientations too. And now the hula hoop is a weird shape. But the hula hoop is oriented so that it is parallel to the field. So the magnetic flux right now is at a minimum, at 0. Now as we rotate it through, so we'll swing it. So this one up here, we turned it this way. This one we're going to turn that way. Okay, so there was no flux through the loop to begin with. But now there is a field pointing down through your loop. So how are you going to oppose that change? We're adding magnetic field down, so the loop's going to do what? Add a magnetic field which way? Up. So you reach into the loop, stick your right hand fingers up, and you grab the wire. So we'll get a current that's going down and back up. All right, so let's look at another case where we can check out the direction of the current due to magnetic flux. So here is a wire. It has been stripped of all of its insulation, so it is a shiny copper wire, and there's a resistor, and then there's some more shiny wire. And now I'm going to take a shiny